Hello. Do you remember the Fibonacci numbers? Maybe you heard them in passing and don't remember what they are, but I'll tell you now. They go 0, 1, 1, 2, 3, 5, 8, 13, and on. You might ask, what's special about these numbers? Well, let's take a closer look. The Fibonacci numbers seem quite random, but upon closer inspection, you'll probably notice that a Fibonacci number is equal to the sum of the two previous ones, like 3, which is 1 plus 2. Now in maths, this is called a recurrence relation, as the function is defined by itself. If we imagine our function for the Fibonacci numbers is f of n, then f of n would be equal to f of n minus 1 plus f of n minus 2, the two Fibonacci numbers before it. But there is one more thing we must include, as the Fibonacci numbers are 0, 1, 1, 2, 3, and not 2, 5, 7, 12, 19, despite both following the recurrence relation. And that is the initial conditions, those being f of 1 equals 0 and f of 2 equals 1. But that still leaves us with one more question. If I want to know the 100th Fibonacci number, or f of 100, then I would have to do 100 sums. There must be a better way. Well, we can graph the Fibonacci numbers and compare them to some common functions. For example, we can try ax plus b, but the Fibonacci numbers are clearly curved. So what about ax squared plus bx plus c? Well, now the Fibonacci numbers grow too fast. In fact, too fast for any polynomial, as they grow exponentially. So, now if we try an exponential function, we can assume f of n is of the form alpha a to the n. If we then sub it into our recurrence, we get this. Now we can divide everything by alpha a to the n to clean things up, and we get 1 equals a to the minus 1 plus a to the minus 2. Now we can multiply by a squared to get this to become a quadratic. Now a squared equals a plus 1. This is known as the characteristic polynomial, and now we can solve for a. We rearrange the equation into a squared minus a minus 1 equals 0, and then use the quadratic formula to get a equals 1 plus or minus the square root of 5, all divided by 2. But wait a minute, we have two values for a. Well, we can actually use both. We'll say a equals 1 plus the square root of 5 over 2, and b equals 1 minus the square root of 5 over 2. And now our Fibonacci function is alpha a to the n plus beta b to the n. Now we just need to figure out alpha and beta. We can use our initial conditions to do that, and we get these two equations. We can solve for alpha to get alpha equals minus b beta over a, which we can sub into our second equation to get this. Then we can solve for beta, making beta 1 over b squared minus ab, or 2 over 5 minus the square root of 5, and making alpha equal square root of 5 minus 1 over 2 times the square root of 5. Now, let's graph this, but why is nothing coming up? Well, since b is negative, its powers are in the complex plane. So, if we want to see the function, we have to take the absolute value. Now that we can see it, yes, it goes straight through all the Fibonacci numbers. It also shows why the golden ratio is involved, as that is the value of a, the dominant term. Anyways, please like and subscribe if you enjoyed the video. I hope you learned something new, and have a nice day.